Hello, my name is Jake Evanston, and this is my everyday physics video assignment. My topic is all about using a reference frame to explore velocity versus time graphs, as well as position versus time graphs and the slopes of these graphs. I will use a mixture of diagrams, calculations, and real-life demonstrations to prove my points. Let's get started.
So in order to understand position versus time graphs, we first have to figure out what position is. So position is the location of an object relative to an origin while using a directional reference frame. So let's use an example to understand this. So we define left as negative and right as positive. And we have this tree where the displacement is equal to 0. So this is what we would call an origin point. And then we have a man standing 10 meters away from this tree. So we would say that his displacement is 10 meters positive because we defined right as positive, or we could display it as displacement equals 10 meters to the right. So that would be his position. So what would happen if we were to graph this last scenario? So saying that it took him 10 seconds to cover those 10 meters, it would produce a graph that looks like this. So with time in seconds on the bottom, and then displacement in meters to the right, because that's the way we defined our reference frame. So this is what our line would be. So now what is the slope of this line? So we know that the slope of a line is delta y over delta x, right? But in this case, delta y is actually delta displacement, and delta x is actually delta t, right? Because that's on the x-axis, that's on the y-axis. So we sub that in, so we get delta d over delta t. And what is the rate of change between delta d and delta t? Well, that's equal to velocity. So that's where velocity comes from. It's the rate of change of displacement over time. So we're going to sub in what we have. So delta d is equal to 10 meters, positive, because it was to the right, that's what we defined. And delta t is equal to 10 seconds. So we get 1 meter per second is his velocity. And then the units are meters divided by seconds, therefore meters per second.
And now for a real-life example. So the object's motion that we'll be looking at is this pool ball. So we're going to define displacement at this point to be 0. And we're also going to define our reference frame as this way is negative, left, and this way is positive, right. All right, and then also the distance that's going to travel is 1 meter from here to here. So assuming that I'm going to move it at a constant velocity, we're going to see its velocity. We'll be able to calculate it from graphing it. So
Alright, so now that we know what velocity is, let's have a look at this next problem. So first of all, we're going to define our reference frame as left being negative and right being positive. And we're also going to define that this tree is at a displacement of 0 meters, or in other words, that's the origin point. And that's where this man starts from. So this guy is running away from this tree, and that's where he starts from. He starts from the origin. And his initial velocity, so his velocity when he's at the tree, is 0 meters per second, which means he's starting from a rest. But let's have a look at his motion running away from this tree. So after 10 seconds of running away, his instantaneous velocity, which means his velocity right at that point, is 1 meter per second. Right? And then another 10 seconds goes by, and his instantaneous velocity is 2 meters per second. And then another 10 seconds goes by, and his instantaneous velocity is 3 meters per second. So now let's have a look at how this would look on a graph. So if we were to graph that situation, it would look something like this. So we have our time axis on the bottom like before, but now we have our velocity axis as our y-axis in meters per second and to the right, because it's still a vector, because it's derived from displacement, which is also a vector, and it's to the right, that's what we defined before. So after 30 seconds, he is now at 3 meters per second. At 20 seconds, he's at 2 meters per second. And at 10 seconds, he's at 1 meter per second. So, what is the slope of this line? Or more so, what does it mean? So we take the equation of the line like we did before, delta y over delta x, but it's actually delta v over delta t, because that's delta y and that's x. And that is equal to a, acceleration. So that's where acceleration comes from. It's the rate of change of velocity over time. So now we plug in our values. So we get delta v is 3 meters per second, and then delta t is 30 seconds, which is 0.1 meters per second. Or if we flip and multiply, because we're dividing fractions, we get 0.1 meters per second squared, as it's more commonly shown. So now that we know what acceleration is, let's plot it on an acceleration versus time graph. So as an example, we'll have a reference frame of left being negative and right being positive, and we're going to do this for a running woman. But this is just to show what an acceleration versus time graph is. So we have acceleration as the y-axis in meters per second
Squared.
and have time on the x-axis in seconds. So it takes this woman 50 seconds to get up to 5 meters per second squared acceleration. Alright, so now let's find the slope of this line. So we take the equation for slope, which is delta y over delta x, sub in delta a over delta t, because delta a is y, delta t is x, and then we find out what that is. So delta a over delta t is equal to jerk, and that's where jerk comes from. Jerk is acceleration over time, the change in acceleration over time. So now we sub what we have. So acceleration, delta a is equal to 5 meters per second squared, and then delta t is equal to 50 seconds. So we get 0.1 meters per second squared per seconds. And then if we flip and multiply like we did before, we get 0.1 meters per second cubed.
So now we know how to calculate jerk, but we still don't really know what it means. So we know that jerk is equal to acceleration over time, but I think a real-life example helps us conceptualize this. So say we have a car starting from rest, and we have an experienced driver behind the wheel. How does an experienced driver drive a car? They step on the gas pedal slowly and constantly accelerate without changing acceleration. So it looks something like this. So you just nice and easy, and now you're going fast, you're accelerating at a constant rate, right? We've all been in this, and you're not doing this, right? Because that would be called jerk. You're jerking back and forth if that were to happen. So if that were to happen, it would look something like this. So you're starting from a stop, and you go off real quick, and then you slow down, and then you keep going, right? So acceleration over time is jerk. So you say that you have a jerky ride in a car if your acceleration is changing. If you start from a stop really fast and you go flying backwards, and then you kind of press on the brakes a little bit and you go flying forwards, that's your acceleration changing. That's what is jerk. Thank you for listening to my presentation. From watching my presentation, you should now be able to define position, velocity, acceleration, and jerk. And additionally, you should be able to apply them to the real world and see the real world through the lens of physics. And you will also be able to graph these values. You'll be able to graph position, velocity, and acceleration. Thank you. Goodbye.